So on this slide we want to record some examples. So the first example is, what is I of Kn? Yeah, so we have this entire space Kn. What is I of Kn? So the answer is 0. So what is the ideal associated with the entire space? So the answer is 0. So we can prove this by induction on n, where n is comes from Kn. But we will only do it for two cases, n equals to 1 and n equals to 2, and you can automatically extend it to further cases by similar methodology or just saying induction. So for the case n equals to 1, and we will stop at n equals to 2. So for case kx, where n is 1, it is very clear, since k is a closed field, every polynomial fx will split into its roots. So you have something like this. Yeah, you have finite number of roots a1 to ad. So obviously this polynomial does not vanish everywhere. So in fact we can find some points at which this polynomial will not vanish. Yeah, so if you choose some other numbers other than the roots, then the polynomial would not vanish. Now for kxy, you can again have a polynomial which we will write as capital F. This you can write it like this. Yeah, so the coefficients are now the polynomials in x. Yeah, so the coefficients a0x is a polynomial in x, a1x is a polynomial in x, a2x is a polynomial in x, and so on. Now by induction there exists some, or we know for n equals to 1 there exist places or exist x where these coefficients do not vanish. So therefore you can always again split this, fix it at a particular number, and you can again split this. Because again k is a closed field, this is a polynomial in y, it gets split, and thus we have a finite number of roots, and that gives us the result. So it has only a finite number of roots, and therefore it cannot be 0 for every xn. The second example is this one. Yeah, this example will come up again and again. So this inclusion is clear. Yeah. Now we want to do the reverse inclusion. Again we will just do it by division. So consider a polynomial f which vanishes at a1 to an. Yeah, so if this vanishes from a1 to an, then you divide it by successively by terms x1 minus a1, then you divide it by x2 minus a2, and so on. So we can write the polynomial like this. Yeah, by successive division plus c, but this term c vanishes on a1 to an, and therefore polynomial, since c vanishes, p is contained in the ideal x1 minus a1 comma x2 minus a2 comma xn minus an. So if we start with f in the ideal and then reach the other direction. Now we have another example where we consider this vanishing set. So we want to compute this. Yeah, we want to compute the ideal of this vanishing set. So this is what we want to compute. Now obviously y square minus x cube is contained in this. Yeah, anything that vanishes on this. Yeah, so this inclusion is clear. We will prove that this inclusion is actually an inequality rather than an inequality, which it looks like this right now. So yeah, you can see it's clear that y square minus x cube belongs to the left hand side. Now any point on this curve is of the form t square minus t cube, where t is an element of k. Yeah, you can just put t square and t cube in the equation and see it satisfies. So pick up polynomial f in IV of y square minus x cube. Now you divide it by y square minus x cube with respect to variable y, and this is what you get. Yeah, now you are dividing it by y square minus x cube, but you are using variable y. Yeah, with respect to y you are dividing. Now obviously we will put t square and t cube, evaluate f at t square and t cube. Then obviously since f belongs to the ideal of the variety, this polynomial will vanish. This is 0, but so is the first term y square minus x cube gxy. So what we are left with is axy plus bx. Obviously we have replaced x with t square and y with t cube, so let us do that here. So you have a of t square, y is t cube, and then similarly b of t square. Now you collect even and odd terms, and we have 0 on the left hand side. So we will have a equals to b equals to 0. And yeah. So instead of this inclusion, we have a equality sign. And that is pretty much it.